Okay. Again, we want to talk about linearized data. We want to know why linearized data is useful. It's because if we've got a graph of our data, so okay, let's just say these points represent data. Okay, that's not going to be population data, because population data would follow an exponential curve. It's not going to be quadratic data. Quadratic data would follow a parabolic curve. This is pretty much on a straight line. Okay? So, here are data points. And let's just call it y and x. Okay, here are data points. We can draw a smooth curve, a straight line through this data. I can take this meter stick and I can lay it along this line, and I can find a line where I've got about as much stuff above as below. Now the actual test is you want the sum of the squares of the distances, vertical distances, between your points and your line to be minimum. Now, I'm not sure where the chalk is going to fall here. Not sure how well this is going to work. Got a little bit more below than above, so I'll put a couple more points above. Okay, now this looks like data seems to be scattered pretty equally on both sides of the line. Again, you might know this if you've had a statistics course. You want to minimize the squares of the vertical distances, as I just said. So when you do it by eyeball, it's a little difficult to visualize unless you really have a good feel for what squares do and stuff. It's a little difficult to visualize it. So you can usually do pretty well by, if none of the points are outliers, none of the points are too awful far from the line, you can usually do a pretty good job of predicting where the line ought to be by making it go through pretty much the middle of your data set. And you want to think of minimizing at least the distance between the line and the points. That's not quite right, but to visualize minimizing the square distance, you're probably not going to want to go to the trouble, because of course you can get your straight line that best fits the data that does minimize those square distances by punching a bunch of stuff into a calculator or a computer system. Okay, into Excel. Does it accurately, does it well. Still, you want to have the visual, and what I stress in this course is not your ability to plug something in to a black box program and get a result. It's your ability to sketch a data set and make your own line, even if it's not totally accurate, and make predictions from that. I don't care at all about using a calculator or a computer or a spreadsheet to get the equation of this line, because you can teach that to a below average 8-year-old in 15 minutes, and I'm exaggerating. I'm just saying it's not a college level skill, being able to put numbers into a spreadsheet and then click on trend line, or punch them into a calculator and stuff. It's a middle school skill at best. Higher level skill is being able to sketch the line, being able to sketch your data set, being able to visualize, being able to understand what that line means. Okay? And of course you can understand what the line means even if you're using a black box. And that's really the highest level skill. So I think it's an overuse of technology at the level of this course to bypass the idea of sketching these things and making your own line and thinking about what it all means. Okay. That said, I'll get off my soapbox and let's see what we do with this. Okay, if we've got a scale on this graph, of course, then we can just pick 2 points on the line and write our function. So if I've got a scale here where x is 15 here and y is 10 here, then I can come over to a point on the line and I can estimate the coordinates of this point. Okay, and I chose to use the x equals 10 or the y equals 10 point. So this, if this is 15, this looks like 12 to me. Okay, and of course this point is 10. Now since the line can be extended to go through the origin, I can, through the y-axis, I can estimate the y-intercept. This point appears to be 0, 3. Now if you've got a good scale, grid and all that, you can make more accurate estimates, but it's clear that you can do that. You're not going to have any trouble doing that. So you understand that if we can sketch our straight line, we can get 2 points on the line, and if one of our points happens to be the y-intercept, that makes it even easier, because now we know that we can calculate the slope based on this fundamental triangle here. And we see that the slope is 7 over 12. And I'm not going to detail that. You know how to do that. And you know what that means. Okay. Well, the slope is 7 over 12 and the y-intercept is 3. So, there we have it. Okay, now, I'm going to kind of cut to the chase for exponential functions. If y equals the log of p, then the log of p equals mx plus b. Now we can use any log we want, and very often we'll use the natural log. But since we're maybe more intuitively familiar with the base 2 log, I'm going to say, okay, let's say this is a graph of log base 2 of p. Okay, so log base 2 of p equals mx plus b. So 2 to the mx plus b equals p. For this graph, 2 raised to the 7/12 x plus 3 equals p. So p equals 2 to the 7/12 x times 2 to the 3rd. Now I'm just using laws of exponents and using them carefully and accurately and thinking to an example so we don't write the wrong thing. We might be tempted, especially since we're dealing with the rules for logarithms, to confuse a multiplication with an addition and write this as a plus. That'd be a very understandable error, although it's an error that I'd penalize severely, because you can always think back to simple examples to verify your laws of exponents, okay? So you don't want to just write down blindly what you think it might be because that's what it looks like. I mean, you're guided by what things look like. Mathematics is largely visual, but you've got to go back to the basic rules and understand where the basic rules come from. It's that simple. So don't be making mistakes like that. Anyhow, this is what you get. So now, P equals 8 times 2 to the 7/12 x, which is then going to be approximately 8 plus 2. Okay, 7/12 is a little less than 0.6, probably about 0.5. 58 x. Okay? And look what I did. I was just talking about putting a plus where you had a multiplication, because that's what it looks like, and I think it's a power of suggestion that nailed me on that one, but there we have it. 8 times 2 to the 0.58x. Now, if I'd have thought to do that intentionally, I would have, just to illustrate, but that was just plain old bonehead mistake on my part. Okay? I looked at it again and just immediately saw it. You want to be careful. That's the message. Okay. Okay, what's our lesson? Given P versus X data, to check whether this is exponential, make a table of log P versus X, log base B of P versus X. For any convenient B. And graph. Well, if you get a table of P versus X, you can do a graph of log P versus X using any base you like. Your graph is then going to be of log base P of B versus X. Okay? If the graph is linear, then do as we just did. To find your exponential function. If not, try log of P versus log of X. We're going to do that and see what that tells us. and it's going to turn out that that gives us a power function as opposed to an exponential function. So you can tell by looking at the data. If the data looks like this, then you got a pretty good idea that you have a straight line. There's some uncertainty in exactly where the line ought to go, but you're going to get a decent model. The more tightly the data points cluster around the line, the better your model is likely to be and the more reliable it's likely to be, to the extent that what you're observing really is exponential. But these points cluster more tightly about the line than these do. And you got this thing called the Pearson R and variance and all that you study in statistics that you can analyze, okay? And I strongly recommend a good statistics course, and we've got good statistics courses. Many schools have good statistics courses. It's a valuable course. Allows you to think about your data in ways that we can't totally address in this course. Also, statistics is quite a bit easier than this course. It's easier, but it's really, really beneficial. Think about it. Okay, so let's see what happens if the log p stuff isn't linear, okay? But maybe the log of p versus log x is linear. So let's start with the log of p versus log x being linear.